So I wanted to thank Bianca and her co-organizers for giving me the chance to speak. And of course, also Bjorn and Angela and Renzo and all the other organizers. I can't see any of them here because the lights are in my eyes. I have some understanding for what goes into running a meeting like this, and I'm just really grateful for them taking up the challenge for making such a great forum for us all to talk to each other. So thank you. So this is in the geometry over global fields, and I have to apologize because there's precious little global fields here. Unless you consider BG a global field, maybe it's the most global field. There will be three parts to the talk. The first is I just want to say a little bit at a very high level about how I think about equivariant birational geometry and some of the key constructions and some of the key peculiarities. I will sort of draw a parallel between the equivariant story and what you see from Galois descent. So it kind of tracks what arguments that you would use over global fields. So I want to develop an analogy. The second part is a very elementary sort of test case to see some of the structures going on. It's work in progress with Tschinkel and Candace Bethea. And the last part will be I will focus entirely on closed fields. And I'm going to take a concrete example, the moduli space of pointing curves of genus 0 to show you some of the results that you can get and how different constructions that you might do from the perspective of classical geometry really inform these questions of birational geometry. Okay, so here I'm going to start with basic equivariant geometry. And so here's the setup. So little k throughout, I hope I'm consistent, is going to be some ground field, which will essentially always be characteristic 0 and algebraically closed. Often I will make reference to another non-closed field for auxiliary construction. That will be capital K. Usually it contains little k. Every once in a while, I'll sort of slip into finite fields. And so just keep in mind, and I hope I was consistent about differentiating between little k and big K. G will be a finite group. We're always going to consider a variety, say a smooth quasi-projective variety with a group action over little k. I'm going to talk a lot about rational maps. And if I talk about a rational map, you should assume it's G equivariant unless explicitly said otherwise. It's just cumbersome to say G equivariant 100 times in the talk. So if I talk about maps, I mean that they're compatible with the action of the group. And finally, this is not something I want to dwell on very much, but if you have a variety with a G action, if you use resolution of singularities, you can always find a nice model that is a smooth projective variety on which G acts regularly. And so if you can always do that. I'm not going to spend a lot of time emphasizing this, but you may as well look into smooth projective varieties with G acting regularly. Okay. So this is part of the dichotomy that I want to talk about. So first of all, birational trivial. We all know what that means when we're working over a field. It means it's AN or PN or something that you can get from AN or PN through some birational modification. So smooth quadrics with rational points, cubic fourfolds with that Sarah talked about. I won't dwell too much about rationality because Sarah did everything for me, so thank you. Equivariantly, what do we mean by birationally trivial? It's actually, well, there's some competing different versions of that. And so you can do exactly what you do. You can say that something is birationally trivial if it's associated with a linear representation of the you have the group acting linearly on a vector space, and vector spaces, they're like affine spaces. And so this is one version of being birationally trivial. Another version is, well, you can let it act on a projectivization of a vector space. And so I'm going to say just this once, that something is strictly linear if it is the action of a group on the vector space linearly, or equivariantly birational for that. And just linearizable if you can get it from the action of a projectivization of a representation. I like projective geometry, so that seems like the natural thing to do. And so already you can see that life is a little bit more complicated, you know. Projective spaces and affine spaces being linearizable in these senses, you know, they're slightly different. The other thing that makes things more complicated is that there are a number of different representations that you could choose. I mean, you know, if you have a large group, you know, SL7 over a field with 243 elements, it's a lot of representations. And so there's no guarantee that these representations have to be mutually birational. I mean, in fact, there's a guarantee that they won't be mutually birational if one of them is a trivial representation and one isn't. So the thing I want to focus on here is that this notion of birationally trivial is not a unitary thing. There are many different representations that I'll think of as being birationally trivial. And so, and in fact, I just want to emphasize, even if you have two faithful representations of the same dimension, they need not be birational to each other. There's work of Cheltsov and probably numerous other people that shows that this is not necessarily the case. So what do you take away from this? Life is better and more simple if you're working over non-closed fields. And I probably should have just stuck to the global field, but there's some interesting things that you get in the equivariant context. So I felt inspired by Timmerman's talk only to the point that I had to have a few bad puns in the headings. And so maybe the whole talk is pointless, but equivariant geometry is definitely pointless. So remember, over non-closed fields, if you have an affine space, you have lots of rational points. The field is infinite, the rational points are Zariski dense. And so if you want to do some construction that works over a Zariski open subset of your affine space, that's all good. You just pick something that happens to be in that subset. Things are a little dicey over finite fields, obviously. You could be unlucky and all of your finite field points aren't available. But over infinite fields, you can find good points to do constructions. Not true. In equivariant geometry, often, usually, representations have no fixed points. Either if I'm looking at it from a honest linear representation or from a projective perspective, there's only a fixed point if you have a trivial subrepresentation or a one-dimensional subrepresentation. Usually it just doesn't happen. And so a lot of the things that you're used to doing in the non-closed field where you just pick your point with a nice property, can't do it. You may not be able to find such a point in the equivariant context. And so, you know, looking at some of the talks from a homotopy theoretic perspective, where instead of taking a given construction, you kind of take a homotopy class of all constructions, equivariant geometry kind of has that feeling about it, because you don't want to take a given construction, you want to take all constructions over some birational model of affine space together in some sense. So there's kind of a homotopic type feeling about this. At least this is what I said to Kirsten over breakfast. So just keep this in mind. There is one thing I want to focus on, the specialties of abelian groups. If you have an abelian group acting on projective space, things are good. One-dimensional representations, lots of fixed points. So this is a unique thing about abelian groups, is that you do have fixed points. And in fact, for smooth projective varieties, under the action of abelian groups, having a fixed point is a birational property. This is a result that I think is due to Reichstein and Usen. So this is the one case where we can use points to sort of say something about birational geometry. So the criterion, the Lang-Nishimura type criterion that was mentioned in Sarah's talk, well, there is kind of a version of it for abelian group actions. Okay.
Is that false? The last statement.
It is false for non-abelian groups, yes. So there are actions for S2 cross S3, where, yeah. If you have a surface fixed by S3 and you blow up, sort of the corresponding P1 doesn't have an S3 fixed point. It's kind of an easiest example. Are there any other questions? Okay, dilemma that has no name. Sounds like a Clint Eastwood movie. So if you have a variety with a group action, and the group acts spatially, this is important, and you have a vector bundle over that variety that is compatible with the group action, then birationally it's trivial. Birationally, it's equivalent to the trivial vector bundle over the said variety. And this birational map can be realized over U. So if you're interested in birational geometry, as long as you have a faithful action on the base, you can replace any equivariant vector bundle with a trivial one. And so this kind of makes things less bad than you would have thought. So of course, it is the case that there are lots of different trivial things, but namely, they're basically all the same. So if I have two representations of the same dimensions, they might not be birational to each other, but if I take them and I add a faithful representation to each of them, they become birational. And so this is one aspect. It probably makes sense to really think about the situation where I don't just focus on strictly linearizable or linearizable. I am a little bit more flexible. And so I take into account this notion of stability, which I think is in the next slide. So over non-closed fields, being stably rational, it becomes rational after taking a product with the vector space. And that definition works pretty well as long as the action on your variety is generically free. Being stably linearizable is exactly when your variety cross affine space is linearizable. If you don't have a faithful action, it's a little bit dicey, right? Because if I have a trivial representation and a non-trivial representation, and I multiply them by trivial representations, they can never be the same. So in general, when you're looking at stable linearizable and you're not assuming that the actions are generically free, you have to allow yourself to tensor with non-trivial faithful representations. And then you get a nice workable category of this notion of stable linearization. But it has one peculiar characteristic, and that is that the stable birational category does not preserve stabilizers. And that's natural given the no-name lemma, but it's a little bit weird. So you can have a trivial representation and a non-trivial representation, they can be stably equivalent to each other because you allow these non-trivial faithful representations to mediate it. Okay. So one last thing I want to say is that there's this wonderful result of Duncan and Reichstein. I'm going to call it the Duncan-Reichstein bridge. It's a really, really nice theorem. And so I spent a lot of time talking about how the Galois side, the non-closed field side, and the equivariant side were different from each other. They differ in important characteristics. But in fact, Duncan and Reichstein built a really beautiful bridge that allows you to go freely from one to the other for the most part. And so let me state this. So suppose that you have a variety with a group action over your field K. The following two things are equivalent. One is that the action is stably linearizable, so the stably trivial action. And now this is a mouthful, but this basically says that if you take your variety and I twist it, I use it to get sort of a variety over a non-closed field. For example, if you have an elliptic curve and you have the involution plus minus 1, you can construct a quadratic twist over any field that has quadratic extensions, just by letting that sort of quadratic Galois involution twist the curve. And so if it's the case that for every field extension, capital K over little k, and every torsor over that, if that twist of your variety, using that torsor is stably rational. That's equivalent to being stably linearizable. So the stable rationality picture and the stable linearization, they're really tightly tied to each other. And so going back and forth from the field picture to the equivariant picture can be really productive. There's one thing about this that kind of sucks, though. I do not know any statement bridging linearizability and rationality. And in fact, I will show you examples where if you just remove like stable from everything here, it's definitely false. And so this is another reason why the naive notions of linearizability, strictly linearizability, they're not the best notions because we can't cross the bridge back and forth from the field world to the equivariant world.
So this second condition, this is when you say stably rational, you're talking about without any group action.
Without any group action. So once I do this twist, no group, yes, thank you very much. There's no, the group is gone. It's just the twisted form, and I'm just thinking of it as a variety over K. Okay. Quadrics. So just to get warmed up, let me show you how some of these ideas work for probably the simplest example of classic varieties. Okay, so by quadric, I mean simply a smooth quadric hypersurface. X defined by a quadratic form. Q, I'm going to think of it as being embedded in some P of V. Throughout, Q will always be non-degenerate. So you know, smooth, simple, homogeneous, everything that you could possibly hope for. But there's a double entendre, so two things that will be tracking in parallel. Over non-closed fields, you think of V as being finite dimensional as a vector space over your non-closed field with coefficients taken from the field. Equivariantly, I want V to be a representation of our group and Q to be an invariant quadratic form under that representation. Another way of saying is that Q gives you a map from B to V dual that's an isomorphism. And so this is a map of the G representations. So the underlying representation of any quadratic form is necessarily self-dual. So that is part of the wash. And so I want to sort of play off against these two perspectives. So let me give you an example of something that's not linearizable. So this is related to the conics that if you were in some of the other rationality talks, but let me explain it. So let's take a dihedral group of order 8, and let's take the standard two-dimensional representation given by these matrices. I hopefully got the matrices right. Sigma, if I square it, I get minus the identity, and that does not act faithfully. It acts trivially on the underlying projective space. And so when I take this linear representation G, and I think of it acting on the projective line, well, let me see. The dihedral group, you don't see this element sigma. You only see the quotient of the group by sigma squared. And so the group C2 cross C2 acts faithfully on PV. And so this group, C2 cross C2, it is not linearizable on the PV. There are no fixed points. So this is not a linearizable act. It does act on symmetric square because you don't see this problem with sigma squared. And I can use this to get PV and represent it as a conic curve in P of sim 2 of V. So I'm basically taking like the Veronese re-embedding of P of V. And so this satisfies the standard equation for a conic curve, UW minus V squared, where these are the invariants. And this is an example of a quadric of dimension 1 that is not linearizable. And so this is analogous to like my favorite conic, the pointless conic x squared plus y squared plus z squared equals 0. For those of you that speak Brouwer, like if this is a two torsion element of the Brouwer group is controlling both sides. This is not important for my talk, but it's probably good to mention that Brouwer elements are important tools for looking at these birational problems. Okay. All right, so now let's go back to our dictionary. A quadric over a field, as they're explained, is rational precisely when you have a rational point. This is the beautiful argument where you project, stereographically project the rational. On the other hand, life is more complicated in the equivariant case. If you are lucky enough to have a fixed point, then you can play the same game. If you have a one-dimensional sub-representation, the variance of the group, for which the quadratic form is isotropic, or in other words, a point on the quadric that is fixed on the axis of the group. Yes, I can project exactly as before. It gives a birational equivariant map from X into this projective space. And so this gives you the linearizability. So yes, if you have fixed points, you have linearizability, but not all linearizable quadrics arise in this way. If you take a product of two-dimensional representations, like the dihedral group of order 2 times 2m plus 1, no fixed points, but you have that this is linearizable because it's a product of linearizable things. So anyway, life is more complicated. Quadrics have a really rich structure in the equivariant case, even ones that are linearizable. And so this is an important, I think, distinction between the geometry over non-closed fields and the variety, the geometry in the equivariant situation. Okay. Another oddly rational or stably so, bad humor. So you can say even more over non-closed fields. You don't need a rational point. Springer has a beautiful theorem that says that as long as you have a cycle of odd degree, 3 points, 5 points, 1,000,001 points, that's enough to force rationality over a field. And so anything, as long as there's some oddity going on, is birationally trivial. Equivariantly, having an odd orbit that's nice, it gets you something. What does it get you? Well, remember, this is the example of crossing the Reichstein bridge, right? We're going to cross the Reichstein bridge. And I want to show you how it's useful in shedding light on these birational geometry questions. So if I follow the Reichstein bridge and I have an odd cycle, if I take any field extension and take a twist over it, because I have an odd cycle, the twisted quadric will have an odd series of points over your field. And so it's rational over K, capital K, which means that it's stably rational over capital K, which means the quadric is stably linearizable. So having these odd cycles, it doesn't give you that they're linearizable, but it gives you stable linearizability. And so this is another indication of why stable linearizability is really the right concept in the equivariant birational world. And in fact, there are examples where you have odd cycles and it's not going to be linearizable. This is really the best that you can do. One nice thing about this is that if you do want to study stable linearizability for quadrics, I just reduced life to 2 groups. I can always look at the group action, restrict to the 2 CELO subgroup, and analyze stable linearizability for that. And so you might say, oh, well, that reduces you to a very small group of collection of groups, except that essentially every group is a 2 group, right? I only learned this through our collaboration. Essentially all groups, if you count them, of a given size, are 2 groups. So maybe this doesn't actually make your life that much easier, but it makes you feel good. You can throw out all the 3 groups, 5 groups, 2 groups are enough. Okay. So some jokes, you just can't stop thinking. So one peculiarity, well, one nice thing about quadrics over non-equal fields is, of course, if you have an isotropic plane, isotropic threefold, you have lots of points, because when your subspaces have points. Not so clear in the equivariant case. I mean, it's possible that you have a quadric fourfold, you have an isotropic plane, but that isotropic plane is a representation that has no fixed points. So you have no, you might have no fixed points. So if you want to look at these stable birational problems, this fixed point criterion, while it's useful, it's not really the natural thing to do. And so the right thing to do is to say, what does it mean for a quadric to have an invariant isotropic subspace of any dimension? And so the good news is that if you have an isotropic subspace, it's always stably rational, stably linearizable. I mean, you can probably see that pretty quickly using the Reichstein bridge, but you don't have any fixed points. And in fact, it very well might not be linearizable. There are simple examples of quadric surfaces where you have lines and you can show that it's not linearizable. So even quadric surfaces, they have some pretty intricate birational geometry. Okay. So I'm not going to get very far in these guiding questions, but this is in some sense a bridge to the future. Like, what are the things that I think are interesting to study? Well, even over, this kind of scandalized me, but even over fields, the birational geometry of quadrics, and this is only the pointless problem is interesting. The birational geometry of anisotropic quadrics is fascinating, intricate. I had no idea. There's a really beautiful paper by Bethea that can show you some of what's known. It gets a sort of high level. There are all these theorems up to dimension 14 or something. It's incredible. I had no idea. And so it ties to a lot of really powerful mathematics, motivic cohomology. This is a huge world. I'm not going to be able to tell you much about it. I just want to make a point that there's a lot of beautiful structure here. So it also makes sense to look at anisotropic quadrics. And so my provisional definition of an anisotropic quadric is one that doesn't have an isotropic subspace. And there's a pretty explicit description of this in terms of representations. The underlying representation is a sum of self-dual representations, each occurring exactly once. And you need to have a quadratic form on each of the pieces. And so this is, one explanation of what an anisotropic quadric could be. Now, I don't know if the homotopy theorists are here, but they might object. Because maybe the right thing is not to say that there's an honest to goodness isotropic subspace. Maybe the right thing to say is that the variety of isotropic subspaces is stably linearizable. You don't need a fixed point. So, there's a question of what we want to say in terms of trivializing the problem. I like this formulation because I actually can test it. I can tell how a group decomposes into representations. Not so sure how to test whether the variety of isotropic subspaces is linearizable. It just takes one harder problem and converts it to another, but that's probably the right way to think about it. In any event, stable birational geometry of quadrics, I think, is a beautiful topic, and one that we're working on. And I just want to give you like one sample result because most of the things I want to talk about are for moduli spaces. This is just the most superficial thing that I could tell you about, but it shows you some of the structure. My favorite field is the real numbers. And so if you take a real quadric, well, from a birational geometry perspective, we only want to look at positive definite or negative definite quadrics. If it's indefinite, you have a rational point. If you have a rational point, it's trivial. But if you want to find a representative of the stable birational equivalence class of every quadric, you don't need quadrics of every dimension. You don't need any quadrics of odd dimension, really. You just need the quadrics with involving, 2, 4, 8, 16, a power of 2 number. And so I don't know whom to attribute this to. I don't know, Pfister, Milner. This is sort of foundational. I'm sorry, I don't know. This is an old result, certainly well known by 1970. So this is just a sample of how the birational geometry works. And so, you get over nice fields like this field, real fields, p-adic fields, finite fields. You can describe all the stable birational equivalence classes pretty explicitly. So this is kind of getting close to global fields, at least local fields. Probably the most similar result I can state for the equivariant case is that if you have a 2 elementary group, C2 cross C2, some number of times, you can kind of do the analogous thing where you just take all the characters of the group, you just, sum up their squares in some way, and you get this quadric on the regular representation. And so we know when these are stably birational. They're almost never stably birationally trivial. And there's a lot of results that you can state that if you start sort of removing some of these variables, but not too many, what you get would be stably birational to the one involving the 2 of the e. So if you have a quadric and it has at least 2 to the e minus 1 plus 1 variables, it's going to be birational to this sort of Pfisterian type quadric. So there's a lot of things that you can say. Most of these are not stably linearizable. They have pretty rich, stable birational geometry, and we're working on this. I don't have a paper yet, so probably that's all I'll say right now. So I'm about to switch to looking at the moduli space examples. So this might not be a bad time to open the floor in case of questions or comments. Yeah, Gina? Leah?
So I have a question. You gave an example of the bridge you can use stable with the 1000% bridge. Then it fails because the second one is true, but the first one is false.
Hold that thought.
Okay.
I will give an example if that's a question.
Okay, great.
Is that the question?
Yeah.
It's like 4 slides ahead. Yeah. Any other questions? Sorry I didn't answer, but I will. Okay, let's continue. So here's a sort of a sample case, twisting moduli spaces. And not even many, G's talk, he twisted some moduli spaces, a million varieties of complicated 3-level structure. Now, we're going to keep it simple. Moduli space M0N, my favorite moduli space. So take P1, take n points on it that are distinct up to projective equivalence. So this is a moduli space. All the rest of this talk, I'm going to be talking about this moduli space. We have a compactification by stable curves, where we just basically allow the P1 to break into components and allow the points to distribute themselves across the various components with a stability condition that you have to have enough points on each component so that there's some positivity. So this is a very standard moduli space that I'm sure many of you have seen before. So these come with group actions because I have n points. I've chosen an order. I can change the order of the points. I have a symmetric group acting on 1 through n. And that symmetric group gives you an induced action on M0n just by rearranging the orders, the indices of the points. And this action extends to the compactification, which is compatible with reordering the points. And in fact, there's a beautiful theorem by Bruno and Miller that says that all the automorphisms of M0 and bar for n not too small, all of them come from the symmetric group. So this is a case where doing equivariant geometry and twisting is sort of laid out for us on a platter because, we have the automorphisms, that's all there are. We can study the problem. So rationality. I want to review why they're rational even over a non-closed field. It's really beautiful. In some sense, it's just the existence of the cross ratio. So if you have P1 and you take 3 distinct points, you can use a unique projectivity to move them to the national standard three distinct points, 1, 0, 0, 1, and 1, 1 in projective space. And if you do that, you can identify M0n with an explicit open subset of P1 to the n minus 3. You just see where the last n minus 3 points go. And this gives you an explicit blow-up realization of M0n bar due to Kiel. M04 bar is P1, M05 bar is P1 cross P1 blown up at a bunch of points. So using these cross ratios, it gives you an explicit realization of M0n bar as a rational variety. But I want to emphasize one thing here. I broke symmetry. Because I told you this is number 1, it goes here, this is number 2, goes here. By breaking symmetry is really essential for getting this rationality construction. And so if yeah, I don't know how to do this without breaking the symmetry. Another beautiful construction that gives rationality of a slightly different flavor is, well, I pin the points a little bit differently. I just pin P1 and P2, and I send them to 0 and infinity. And I let all the other points float freely. So the other n minus 2 points, they go wherever they want. Now, that's a little bit unfortunate because it gives you something that's a little bit bigger. N minus 2, the number of free points is bigger than the dimension n minus 3. But then I just let the torus, fixing 0 infinity, rescale the points. And then I sort of rigidify everything. And so this is a different way to skin the cat and get a rationality construction. And if you think about it, there's a different symmetry that's involved. I'm partitioning the n points into 2 points and n minus 2 points to get this construction. And so every construction that I know of to understand the moduli space explicitly, you're going to break symmetry. And so that's just part of it. Here's another construction where I get a birational map. I don't think I can do this justice given the time. You have a birational map from n0n to Pn minus 3, basically using the geometry of rational normal curves. And this construction, it singles out just one of the points. You just take one of the points to get this. And so this realizes M05 not as a blowup of P1 cross P1 at 3 points, but as a blowup of P2 at 4 points. So in all these cases, you're kind of you're breaking symmetry to do the rationality stuff. All right, so this is, I think, what I just said. Just to be explicit about, for the 3 rationality constructions in each case, you broke the symmetry in an explicit way. All right. One sort of curiosity is that when you change how you break symmetry, you get some interesting birational geometry. You get from M05, you get different maps to P2, and comparing those different maps is kind of fun and interesting. These are, this is how a moduli theorist would do Monis transformations. Monis transformation is an explicit example of this. All right, I will come back to this. But basically, this is, I want to be a little short here. If I have n points in P1, I can think of them as like columns of matrix, just by taking the coordinates. And I can think of the linear group acting from the left, a torus acting from the right, and this gives you another way of getting a birational model. So I'm basically getting the orbits of points as a sort of a double coset space. And I like this because I'm not breaking symmetry. Here are all the points being treated on the same basis. If I permute the columns of this matrix, nothing really changes. How I think about the torus, how I order the coordinates changes, but this is a construction that is actually equivariant with respect to the symmetric group action. All right. So here's the question I want to answer. Remember this Reichstein game that we played where if I have a Galois extension, I can use it to twist the moduli space. So here, if I have a map from the Galois group into the symmetric group on n letters, I can twist. This is the same twist as we were talking about before, essentially. And you get a whole plethora of different moduli spaces. If I pass the field extension, they're just M0 n bar, but they're different over the non-closed field. And so I can interpret this as moduli spaces of pairs consisting of a sort of a tree of genus zero curves, a cycle Z, where the cycle Z has length n, and the Galois group permutes the points on n in a prescribed way that I've designated by this tau, this representation. So my question is, when is this rational or stably rational? When I start twisting, for which of these moduli spaces do you get something that is birationally trivial? If it's trivial, I've shown you via the Caprana, but via the Kiel construction that it's rational. But if the Galois action doesn't respect the partitions, it's not so clear. All right. One example, 4 points. 4 points is fun. I take 4 points. I put them in the plane. I can let the Galois action spin them around. And then if I just take all the conics through those 4 points, that's my moduli space. It's always P1, and I don't care how it acts. So this, however you twist for 4 points, whatever action you get, it's just the conics, pencil conics through 4 points. It's always P1. So this is one case where you think, well, maybe this is kind of a boring question because the first case you look at, nothing happens. So anyway, I like this example, but another example is that when you take M05 and you twist it, however you twist it, you always get something that's rational over an unclosed field. And so this is a beautiful argument. It goes back to Enriquez, Swinnerton-Dyer, Skor-Bogota. There is a nice Schubert calculus proof for, maybe Ravi will like the Schubert calculus proof, intersection theory and Grassmannians. But there's also a really explicit classical geometry proof. I don't want to dwell too much about this because I'm running low on time. All right, now, Lena, I think I'm going to pay my debt to you now. So if you look at M05, over a field, it's always rational. But the S5 action on M05 can't be linearizable because it's kind of hard to find a two-dimensional projective space with an S5 action on it. We don't have there's just no representations available. There's no way there's no candidate representation. So M05 is not linearizable for the full group action. And so, things are more complicated. The Reichstein bridge tells me it's stably linearizable. And so when we're working in the equivariant category, the stable linearizability is really, again, the right thing to consider. Now, finally, I'm just going to go into the global fields or arbitrary fields. I'm not going to talk about equivariant geometry anymore. To get to the end, I'm just going to push through and do sort of the non-closed field case. But everything that I say over non-closed fields, if you just take the bridge that Duncan and Reichstein have said, there's an equivariant statement as well. All right. Florence and Reichstein. As long as you have an odd number of points, it's rational. On the other hand, there are non-rational examples that they give. You construct it using Brauer groups. And so if you have an even number of points, say 6 points, it is possible to find examples that are not rational. So they're not all rational. M04 is the aberration. Any other even number of points, not rational in general. And I'm going to come back and give an explicit construction of this in a moment, but we do have examples of these things that are not rational. And this construction uses some nice results on Brauer groups. It does make pretty stringent restrictions on the field. And so I could drop a lot of these things. This is one nice thing about equivariant geometry is that generally it gives pretty broad statements that don't care too much about the field as long as you specify the Galois action. All right, so some theorems. So let's see. So in general, over an arbitrary field, I specify the representation and let y be the twist. All right, I'm just basically going to review what we got from Kapranov, Kiel, and Losov-Manin. So Kapranov's construction, if T factors through the symmetric group on n-1 letters, if it fixes some point, then it's rational over the ground field. If it preserves the decomposition into Sn-3 and S3, it's rational over the ground field. If it has an odd orbit at all, it's at least stably rational. And so if it factors through S2 cross Sn-2, well, I don't quite know, except that there is a criterion for testing stable rationality. This is a toric variety. As a toric variety, there's a criterion for stable rationality in terms of Galois representations. As long as the action on the Picard group is stably permutation, as a Galois module, it's stably rational. And I wish I knew how to test this algorithmically. Probably one of you can tell me how to do it. But at least in principle, this reduces the rationality question for the Losov-Manin twists to a computation in Galois cohomology. Whether they're rational or not is interesting. Okay. So one of the invariants you can use is to look at the Brown group or the Galois cohomology on the Picard group. If something is rational, as I mentioned, it's stably permutation. And so the Galois cohomology on the Picard group has to vanish. And so I can cook this up as long as you have a biquadratic extension. Take any field that has a biquadratic extension, and for any even n, there's a twisted form that is not rational. This copy of the Klein 4 group with this permutation action is the simplest instance, but there are infinitely many. And so this is applicable whenever you have a biquadratic extension, even in fields where there's no Brown group. I mean, Brown groups are really cool and all, but I don't need a Brown group to do this. At least not a Brown group from the field. Of course, there's a Brown group on the right that we get from this H1, but I don't. This works over a function field of complex curve. Okay. Here's some other results. We get a complete description of a rationality for 6 points in terms of how it acts and what gets fixed and not fixed. All of the stably rational examples are actually rational, so it's not that exciting from a stable birational perspective. The easiest way to see these constructions is to use the Segre threefold model, a cubic threefold with 10 nodes with symmetric in the S6 action. So we have a pretty complete picture for M06. All right. So we have a new proof of the Florence-Reichstein result. And so if you have an arbitrary field in the twisted form with an odd number of points and this rational over K, this works even over finite fields. The Reichstein-Florence proof insisted that the field be infinite. So there's a slight generalization. And it uses this symmetric property of the Gelfand-McPherson construction and some really nice Schubert calculus. So I like this argument as an alternative approach. And it works even when the field is really small. So, I mean, if you have a twisted form, you might not have any smooth rational points, right? So, you know, it's just kind of, it's nice to be able to do this without having the rational points. So another result, if the action sort of partitions into two groups of points in a nice way, you can get rationality. So let me just point you to the thing here. The best result of this is that if you do it over R, always rational. So any M0n, if you twist by R, so if you take your 30 points and you have 15 complex conjugate pairs, if there are real points that are real mark points, obviously we know that it's rational. But we have forms over R, forms over cyclic groups that are barely even, 2 times M order, where M is odd. They're all rational. So we get a whole bunch of examples here of rational examples. All right. I'm sorry, I'm out of time. This is my last slide. Questions? I am embarrassed to say I don't know what's going on for cyclic extensions. I think that this is probably doable. Surely the Galois cohomology is doable, and I'm embarrassed to say I haven't done it yet. But if you have a cyclic group, if you have a twist of M0n over a finite field, I don't know whether it's rational or not. The Galois cohomology tricks that we do, I don't think they work. Are there any non-rational, stably rational forms? That would be really cool. Don't know. If you have an orbit, does it guarantee rationality? We know it guarantees stable rationality, but we don't know about rationality. In any event, these are some open questions, and I think that's all I'm going to say for now. Thanks for your patience.
Thank you for the very nice talk. If you look in your exposition at the start, comparing the sort of non-closed and equivariant case, that the information usually kind of flowed in one direction from the sort of non-closed case to inform the equivariant case. You know, in many situations where the other way kind of works, or knowing good stuff in the equivariant case kind of tells us more about the non-closed case.
There were results. I mean, all the proofs I presented here, that's basically equivariant proofs. So the arguments here are equivariant. I mean, one example of a statement like this one here, having an odd orbit, forcing stably rational. Whenever you see a statement like this, you should say, we're crossing the Duncan-Whiteside bridge. So, I mean, I guess if I worked hard, I could probably do it, in such a way that it just ignores the bridge, but I think it's the most transparent way to see it. So, I mean, the argument that we wrote down really does use equivariant techniques. So, yeah, if you see stable rationality as a result, you're probably thinking equivariantly rather, but since you have the bridge, you cross it, and then you cross it 3 or 4 times, once, right? So, yeah, but for this statement, I see it primarily as an equivariant, the last statement. With Ben? Yeah.
Yeah, thank you for the talk. This is kind of a random question. Maybe there's not a good answer to this, but in the M06 case with the quadric extinction,
Yeah.
Is that connected to the on1 or somehow? I mean, like,
Certainly if I look at the proof here, it goes in that way. I think if I remember correctly.
oh, that serves, but not the one that's not.
I mean, it's not that different. But I mean, the proof that we use, we probably, this is really basically like a computation. You write down the basis, you write down the action. If you and then you basically, you say, oh, this is wrong. But I think that topological computation, it probably is related to a norm torus computation. I think that the computations are more or less the same. It's just that this approach it is a little less finicky. I mean, I need to know less about the field. But I think if I were to translate it, it would probably be pretty similar to one. That's not too bad.
I was thinking if I could ask you another question.
Yeah.
So, with the kind of untwisted and zero in, you have this kind of McPherson thing, which you were mentioning, or the Gelfand McPherson.
Yeah.
And so is there like a kind of a twisted one where you have like where you have some, where you could think of it as a quotient by some torus on the last step that's.
Yeah, let me go to. Yeah, so basically, I think I have my latest slide, but what I do here, get this to work, is I do everything that I showed you, except that I left the P1s have a non-trivial Galois too, if you read it around, and then this torus is not split torus, it's a non-split torus. So I let the normal plain old Grassmanni have this torus action. Probably I wrote that down somewhere. Oh, there it is. Yeah, so that's the argument, is that we basically count the Grassmannian fix and think about the torus as a totally twisted data. And so it kind of gives you a uniform way of tackling. And to the extent you can see this when we intersect the and the Grassmannian, it kind of makes it transparent, because Schubert, like the Schubert cycles, you can see it pretty clearly. Sometimes it can be hard to find linear subspaces in the equivariant case, and so the equivariant version does a little bit. Yeah, thank you.
There are no other questions, that's time to run it again.
Thank you.